Inscribed angles is our topic. We're going to learn lots of stuff about inscribed angles. There will be two theorems and a bunch of corollaries from one of the theorems. So first of all, we're going to define for you what an inscribed angle is, but let me show it to you. There are two examples of inscribed angles. And this is how we define it as you expect it to be. This is how just as you might have expected. Inscribed angle is an angle whose vertex, whose vertex is on a circle and whose sides contain chords of the circle. So both of these, the vertex is on the circle, and look at the size of these angles. They're chords, right? So that's how you get an inscribed angle. And as you can see, inscribed angle 1 intercepts the arc right here. You see the minor arc? It intercepts. What about the inscribed angle 2? What kind of arc does it intercept? Minor or major? It intercepts a major arc, doesn't it? So, as we talk about, we had central angle intercepting an arc. We could also have inscribed angle intercepting an arc as well. Okay. So write that down. An inscribed angle is an angle whose vertex is on the circle, and whose sides contain the chords of the circle. And inscribed angle 1 intercepts the minor arc. Inscribed angle 2 intercepts the major arc. Okay. So write that down. So what we're going to learn today, we're going to learn the theorem that compares the measure of an inscribed angle with the measure of its intercepted arc. Okay, so we're going to talk about the measure, the relationship between the measure of the intercepted angle and the intercepted arc. It turns out, you learned this in the intro. Let me see if you recognize this theorem. It says the measure of an inscribed angle is half of the measure of its intercepted arc. Was it? Very good. So then you should recognize, here's a picture. Let me move this off for you. There are actually 3 cases if you wanted to prove this. We're going to talk about case 1 for now, but all the other 2 cases, you could use just case 1, where the center lies on one of the one of the chord of the angle. But C doesn't have to be on the side of angle. It could be inside it or outside of it. But really the important is case 1. With this case 1, you could actually, when you prove case 2 and 3, you could draw another, you could actually draw a diameter here to help you prove the rest. So, but we could talk about that when we have time. But right now, we're just going to talk about case 1 where the O lies on angle ABC. So, by the way, what is it saying? The measure of an intercepted angle is equal to half of the measure of its intercepted arc. One person see? That's it? Okay, how about 2? How about, let me ask, what do you think this means by the measure of an intercepted arc, intercepted angle, inscribed, sorry. The measure of an inscribed angle is equal to the half of its intercepted arc. What do you think this means? How about, give me a sec. Shanna, what do you think this is talking about? So measure of an inscribed angle. So in this picture, what is the inscribed angle in this picture? Angle ABO, ABO, ABC. Yeah, well, yeah. Inscribed angle. Remember, we just defined it. Inscribed angle, its vertex is on the circle, and then you have the 2 chords here, right? Does that make sense? So that's what makes an inscribed angle. So angle ABO. What are they saying? ABO, ABC. What is this angle equal to? They said this angle equals to what? Half measure of its intercepted arc. Which is the intercepted arc of this inscribed angle? Arc AC. So look, if AC happens to be 100 degrees, guess what angle B is? 50. That's all they're saying. That's all they're saying. It's half of it. Right? If this intercepted arc, right, is 100 degrees, guess what angle B is? 50 degrees. That's all they're saying. What if this angle intercepted arc is, I don't know, 50 degrees? What's the intercepted arc cost? I mean, intercepted arc is 50. The inscribed angle is 25 degrees. It's half of it. If the intercepted arc is 140 degrees, what is the inscribed angle? 70, half of it. What if this measures x degrees? X over 2, right? Easy enough? Okay, so does it have to look like this where one of the side hits the center? No, it could be any other two cases. They divided it this way so that you could prove this. What if, let's see, what if in this case too, what if the inscribed angle is x degrees? What is going to be then the measure of it's going to be twice as much, 2x, right? You could think of it that way too. Easy enough? Does that make sense? So let's think about then how you go about proving this case 1. As I said, if you know how to solve case 1, you could use case 1 to solve the rest of these by drawing an auxiliary line. This time it will be a diameter, right? That will go through the center. Anyway, so how would you do this? How can you show? By the way, do you think that dotted line is going to be helpful for us? Turns out it is. So let me give you a hint. Let's call this angle ABC x. Is that okay? What would happen then? If this is x, we want to show that arc AC is going to be what? 2x. Is there a way to do that? Go ahead, everybody think as a group. How can I show that arc measure AC is twice of this angle? So if I call this angle ABC x, how can I know that measure of the arc is twice of 2x? Okay, go ahead, everybody think about it. So how would you go about proving this? Case 1, I drew it again for you. So we said let this angle to be x degrees. Is that okay? And yes, here's the auxiliary line right here. If we call that angle x, there's another angle that measures x. Who could tell me what that is? How about Jordan? Angle A, right? BOA, good. This angle right here is also x. Why should that be also x degrees? How about Reagan? Good, all radii are equal, right? Congruent. So therefore, what kind of triangles do you have, basically? Isosceles. So by the isosceles triangle theorem, what do you know about its base angle? They're congruent. Is that okay? So, but that's not what we wanted to prove. We wanted to show that the measure of this arc AC is twice of this angle x, which has been 2x. But what do we know about the exterior angle of a triangle? How about Narek?
Yes. So the exterior angle is equal to the sum of the interior angles.
Sum of the two remote interior angles, right? Because this is an interior angle too, but we want the two remote. So yes, this angle right here. Do you guys remember this exterior angle is twice of? Is sum of the two remote interior angles. What's x plus x? 2x. Now if that's 2x. Thank you. Hold on. Just wait. If this is 2x right here. What do we know about this arc, AC? How about Hannah over here in the back? Yes. Yeah, this is also going to be 2x. Why, Hannah? By the... not the theorem. It's actually... It's a definition of what, Hannah? Definition of... measure of minor arc. Which states what, Hannah? What does it say? Yeah, the measure of the arc is equal to the central angle. You guys remember that? So if the central angle right here, isn't this a central angle? AOC. So the measure of this arc must be 2x as well. Do you see how that you could prove that? And of course, actually proving this theorem, you have to go through the other two cases. You could think about those later. Okay, but right now, if you know how to prove the case 1, you could actually draw an auxiliary line, diagonals over here that goes through O, and you could actually use case 1 to prove the rest. So anyway, that's how you do that one. Okay, so knowing this, then let's do an example. Okay, so everyone go ahead and try example 1. Here's a picture. Knowing that theorem, theorem is really useful. You could actually figure out what the measure of x is and what the measure of this y, the arc measure y is. Go ahead, everybody. Go ahead and try. I'll wait. Okay. Everybody. Here we go. How about Josephine? What do you think? What would you like to find first here? So let's find the value of x. What would the value of x? Let's do that in alphabetical order. 20 is correct. How many people agree with her? That's 20. Very good. It's because the intercepted arc is 40. X has to be 20. There you go. Okay, 20 degrees. What about y there? How about Jack? What do you think?
Yeah.
What should we do here?
The whole arc PR
Yes.
is 100 degrees.
Good. That's important to note. This whole thing here is 100, right? So we're not talking about just y part. The whole thing is 100. Therefore,
So then
because you know this is 50 is twice of it, right?
Yeah.
So therefore, what's y?
You subtract 40.
Yeah, y is 100 minus 40, which is
60.
60. Okay, does that make sense? So many times, guess what people give me? Instead of 60, they give me 100. Okay, we're not talking about this whole thing, are we? We're just talking about the y, which is part of it. Does that make sense? Very good. So let's move on to, we get 3 corollaries that comes from this theorem, which are pretty straightforward. So let's take a look at these. Okay. So the first corollary we get says, if 2 inscribed angles intercept the same arc, guess what? Then the angles are congruent. Here's a picture. And you could show this very easily using the previous theorem. So take a look at this picture and look at what it says. If 2 inscribed angles intercept the same arc, you see how angle 1 and angle 2, they intercept the same arc down here?
Yeah.
Okay? When that happens, you know that angle 1 and 2 are congruent. Now, would this be true? This is very easy to show. Let's say this intercepted arc is 2x. What's the measure of angle 1? What is it? X. What is measure of angle 2? X. It's sharing the same arc. Does that make sense? So, if the 2 inscribed angles intercept the same arc, then the angles are congruent. That's easy, right, to show. Okay. All right. So write this down. You don't necessarily want to memorize these corollaries, right? They should really make sense to you, right? So if you really understand what it's saying and you know why that's true, really remembering should be easy enough. Take a look at this one. This is actually easy to remember too. An angle inscribed in a semicircle is a right angle. Why should this be true here? Here's a picture. Why should an angle inscribed in a semicircle? As you can see, this angle MXN is inscribed in a semicircle. You see the semicircle on top?
Yeah.
Why should this angle X be 90? Reagan? You're exactly right. So therefore, if this is semicircle, what is the arc measure of this other semicircle here in black? 180. And therefore, isn't this an inscribed angle that intercepts the arc that happens to be 180, which is semicircle? Guess what? X must be 90. So that's what it's saying. So if you understand the theorem, these are trivial. Does that make sense? They really come from that theorem. You shouldn't have to really try to memorize them. You should just understand these things, right? You should be able to understand. And if you understand them, it's a lot easier to remember. Okay? So take a look at this corollary. This one is sort of interesting. Look what it says here. If a quadrilateral is inscribed in a circle, so this time you don't have an inscribed angle, but you have a quadrilateral, then its opposite angles are supplementary. So here's a picture. Notice the quadrilateral does not have to be a rectangle or square or anything like that. It's any quadrilateral you want. Okay, and so as long as it's inscribed in a circle. In other words, all the vertices are on the circle. Turns out, if that's true, the opposite angles, E and G, when you add these angles together, guess what? It equals to 180. F and H, when you add them together, it equals to 180. Why should that be? Some of you see it. I want you to think about this as a group, because this one's kind of interesting to think about. Go ahead. Why should this be true? Go ahead. Everybody think about this. So I drew this again, and as you can see, my quadrilateral, right, is inscribed in a circle, right? So let's call this angle F X degrees. Is that okay? If I did, thank you. If I did, you know that you see here's the inscribed angle. You see the inscribed arc. What is the measurement of this inscribed arc in blue?
2x.
It'll be 2x. Wouldn't that be? Isn't that right? From the previous theorem, we know, right? This is an inscribed angle. Therefore, it's inscribed arc, right? It's twice as much because the other way is true also. Correct? Now, if that's true, what can you tell me about the measurement of this, the other arc, GFE, the one in red? What is the measurement of this GFE? Is it 180 minus 2x or 360 minus 2x? This will be 360 minus 2x, wouldn't it not? The GFE, right? Right there. Because the other side is 2x, it's got to be 360 minus 2x, right? What is then the measurement of this inscribed angle, GHE, that intercepts the arc GFE? How about, who could tell me this? How about, this is actually using this theorem straight. Emily, what would the measure of this inscribed angle GHE be if its intercepted arc is 360 minus 2x?
I have no idea.
Okay, Emily, watch this. Let's say I have a circle, right? And I have an inscribed angle right here. Let's say this intercepted arc is 100 degrees. What's this angle? 50. You know that, right? What if this was not 100, but what if it was x? What would this be? Yeah. So now instead of x, what do I have? 360 minus 2x, right? So guess what this angle must be? 180 minus x. All right. Now when you add them together, what do you get, guys? 180. So they are supplementary to each other. And you could do the same for angle G and E, can't you not? So it works the same way. Do you see what this theorem is talking about now? Right? In a quadrilateral, okay, if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. And do you see why the previous theorem really is, right? Why this is a corollary of the previous theorem? Does that make sense?
Yes.
It uses us straight. Okay, let's do an example then. Knowing all these corollaries and so forth, go ahead and do this example 2. Hold on. Go ahead and find the value of x, y, z. Here's a picture. You should all be able to do this without much problem. By the way, look at angle z. Is this angle z talking about just angle ABC, or is this talking about ABD? Angle ABD. I mean, sorry, BAD, right?
It's talking about BAC.
Yes. No. This angle z is not BAC. It's the BAD, the whole thing. You see how it's going through the whole thing? So that's what they want you to find. Okay, z, because some of you thought that z was, right? BAC. It's not BAC, it's BAD. Does that make sense? Go ahead, everybody find the values of x, y, and z. I'll wait. Help each other out as a group and so forth. I like this problem because it's one of those problems where if you don't see it, like, it can be really hard, but not really, okay? Because take a look at, let's look at x first. Take a look at the angle x. Look at the intercepted arc of angle x. It is what?
AB.
The intercepted arc of the inscribed angle x is AB. Would you not agree?
I would agree.
What about the intercepted arc of angle ADB?
Maybe.
It's also AB. That's the key. Okay. Okay, so a lot of you are having trouble. Okay. You see how? Okay. You see how both of these intercepted arc, both of these inscribed angle intercept the same intercepted arc? Okay, so therefore, listen. Therefore, x has to be what? X has to be 40, correct? Because, okay, what if I ask you for the measurement of this intercepted arc? What is the intercepted arc then? The measurement of the intercepted arc.
80.
Thank you. It's not 40, it's 80, okay? Right? Because this, right, if this is 80, that's, this intercepted angle is half of it. Inscribed angle is half of it. Does that make sense? So that one you have to really look at carefully, because both of these, okay, on your homework tonight, you're going to see many of these inscribed angle would intersect, intersect the same arc. Okay, when it does, you know that they are congruent, right?
Yep.
That was our first corollary, right? If two inscribed angle intercept the same arc, then they're congruent, correct? So that's how we know that x is 40. What about then y? Y is actually pretty straightforward, because let me erase these. Okay, so yeah, because who could tell me, how about y is one of the easier one to figure out? Jason, what's angle y going to be? 90, you're right. Why would it be 90? Yeah, look, angle y is inscribed in a semicircle, isn't that right? Or you could see the other side. This is 180 degrees, this intercepted arc, therefore this has to be 90. Okay, so we're good with x and y. Now, how do you figure out what z is then? Okay, to find z, it turns out it's pretty straightforward. If you remember the last corollary we just learned. How about Kenneth? What do you think?
Z is opposite.
Is z opposite of x?
Angle Z is opposite of ACB. Because corollary
Good. So what is this whole angle here? If this is 40, if this is 30,
that's
this is going to be 70 degrees. So therefore, angle z must be, yeah, z plus 70 must equal to what? 180. So z, they're supplementary. So z must be 110. Do you see how we get that? How we got this? All three of them correct. Does this make sense? Okay. If you didn't, do you understand why? How we? Okay. Good. Okay. All right. Let's take a look at this example here. This is going to illustrate what our next theorem is going to be. This is our last theorem of this section today. Take a look at this picture. What do you think the angle measure of t will be if the measurement of this intercepted arc AB is x degrees? No, it's not. It's the same exact thing we did. Okay, it's half of x, right? Would you not agree? If the intercepted arc AB is x, the angle t is half of x. What if I move b down here? Does it change anything? No, it's the same thing, right? You have an inscribed angle, right? If the measure of AB is x degrees, then angle t must be half of it. Would you agree?
Yes.
What if I now move b a little more towards t? Would it remain the same? Yes, it would. Look, if this if the intercepted arc is x degrees, this inscribed angle is half of that x. Now, what if I put b all the way to c and you get this picture? And you get a tangent, don't you?
Yeah.
So you basically have a chord and a tangent. Does that make sense? What do you guys think the relationship of this intercepted arc versus this angle where you have the tangent and the chord makes? Does it have to be 90? The answer is no. It will be 90 if this is a diameter. Then it'll be 90. You guys remember? We learned that last time. But this is not a diameter, is it? It doesn't have to be. Anybody want to guess what the relationship might be? Let's say the angle measure of the arc AT is x. What would the angle AT be? This angle be? The chord and the tangent make? Yeah. It'll be half of x, just like all the other ones. So it turns out, it is also, this angle will be half of this intercepted arc. Just like all the other ones. Look, what was this angle t again? If this was x? X over 2. What is this angle t when x over 2? Guess what? If this is x, guess what? If this is x, this angle is also x over 2. Okay. So somebody read this for us. Applying theorem 9.7. This is summarizing what we just talked about. How about, let's read this. How about, Leah, can you read this for us?
Apply theorem 9.7 to diagrams 1, 2, and 3, and you have measured angle t equals to 1/2 measure of arc AB.
Yep.
As you might expect, this equation applies to diagram 4, 2, since we say that angle t intercepts arc AB in this case as well. Diagram 4 suggests that theorem 9 and 8 in exercises 13 through 15, you'll prove these three cases of the theorem.
Okay, so that's left for you as an exercise. But here is a theorem, as we just talked about. The measure of an angle formed by a chord, AT, and a tangent. You see how they form an angle? Right? The chord and the tangent, they meet at T right here. The measurement of an angle formed by the chord and the tangent is equal to, just like the other theorem, is what? Half of the measure of the intercepted arc. Do you see how it's very similar to the first theorem we talked about today? Right? Right? So it follows the same way. Just like the measure of an inscribed angle is half of the measure of its intercepted arc. Here, we don't have an inscribed angle, but we have an angle formed by a chord and a tangent. It works the same way. It's half of the intercepted arc. Okay? So take a look at that example underneath. If this arc AT is 140 degrees, what would the angle ATP be? Class? 70. It's half of that intercepted arc. Is that okay? Does this make sense?
Yes.
So, can you use these theorems and corollaries to do your homework tonight?
Yes.
Do you understand what they're saying?
Yes.
Okay, very good. Okay.